I have a great talk to introduce. This is one of the ones that I really like reading. And it is EVM, who's going to be taking us back 45 years in the USSR to talk about old technology and how to reverse that. Take it away.
All right. Thank you, everybody. Thank you, John. So I'm EVM, and I'm going to be talking about Elbrus, which I've been looking at for a little while now. Here you can, a couple of things before we get started. So you can follow me on Twitter and Mastodon there. There's my handles. This URL here, github.com, EVMsec smashing vpointers. All of the code that I'm going to be walking through today is there on the GitHub page. So if you want to follow along, you're welcome to do that if you brought your laptop. Got both the source code and the Elbrus disassembly in that repo, so you can kind of walk through and check it out. This is just a little bit about me. So I work at Johns Hopkins Applied Physics Lab. Yeah, woo. Represent. So I've been involved, worked there for a really long time, about 18 years, and do a lot of stuff with reverse engineering there. I have started to kind of branch out and engage in more kind of public reverse engineering projects. So you may have heard of the All-Star data set, which is about trying to apply AI to reverse engineering. I work on a project called CodeCut, which is about organizing object files within Ghidra. Worked with Travis Goodspeed on SimGreat, which you may have heard of. In my free time, I still can't stop reversing and hacking, so I hacked a baseball scoreboard and wrote control software for it. I teach in the Johns Hopkins EP program. I teach at APL, and I also teach in 4-H. I teach my kids how to program sometimes. I forgot to mention, I'm giving this talk under extreme duress because all of my kids are here in the front row, heavily armed with shmoo balls. Thanks. So that'll be happening. I should say, so I'm a Jesus follower. Jesus says in Luke that there's nothing hidden that won't be revealed, and that those words are extremely encouraging to me as a reverse engineer. So that's kind of my motivation for RE. Just a little bit about APL. A lot of people haven't heard of us because they think of Johns Hopkins. APL is like a DoD university research center. We're located in Laurel. We're really big place, kind of like a national lab if you're familiar with national labs. UARCs are a little bit different, but same kind of idea. Most people know us from, if they've heard of APL, they've heard of like the New Horizons missions that went to Pluto. Like, so we have a group of people that build spacecraft, but we also do fun reverse engineering and offensive cyber stuff for the DoD and IC. If that sounds interesting to you, we're heavily hiring because we've got a lot of interesting challenges in that field. So, feel free to talk to me about that later. Okay, so let's talk about Elbrus. Elbrus is really interesting because it is one of the Russian microprocessors where the architecture itself was developed in Russia, right? So we see these things with Russia and China where you have microprocessors that are developed in those countries, but a lot of times they're an architecture like ARM or MIPS that is, somebody else developed and they're just implementing that architecture. But Elbrus is actually a Russian designed architecture that goes all the way back to the late 70s. Okay, so and we're going to see that Elbrus is kind of a unique, sort of like a fossil, really, in sort of architecture, because it's kind of got an architecture that doesn't really exist anywhere else anymore. So there is this thing called the the Lebedev Institute, and they eventually kind of spun out this thing called Moscow Center for Spark Technologies, MCST, and that's kind of the company that still produces Elbrus today. So if you think back to the 70s, this is when Intel was kind of, getting off the ground, and we were starting to think about, can I do, so we have we had this idea of scalar processor pipelines where each instruction goes through linearly in the pipeline, and so Intel was starting to think about how can we do this with out of order execution, so we execute things in parallel so we get more efficiency, right? And so this same thing was happening with Elbrus, in Russia at that time. And we're going to get into kind of how they design that and why it's similar but different to Intel. It's currently manufactured by TSMC. Russia, as far as we know, only has 90 nanometer manufacturing technology inside the country. So, they, like everybody else, they go to Taiwan to get their stuff manufactured. We were watching Armageddon in our hotel room last night, and in Armageddon, there's the Russian guy who says, like, American components and Russian components, they're all made in Taiwan. That's still true. Like, everybody manufactures their chips in Taiwan, right? So there's a bunch of different models available. MCST, because of the Russian invasion, ended up on the sanctions list, and so TSMC actually isn't producing them anymore. I'm not really sure what is going on with that, like if they have a different, different group that's producing them. But as far as I know, they're not really making new ones. That the Russian invasion and the sanctions that unfolded because of that really kind of screwed their plans. I don't know if I have mentioned the 16 core model. I have no idea if that ever got out there. We thankfully, for this talk, there were kind of a group of people that before the Russian invasion decided, hey, let's go out and buy one of these things. And so I basically just got a shell account on that thing and got to kind of play around with it. So we did acquire the hardware pre-sanctions. No sanctions were violated in the making of this talk, right? Okay. Whoa. Thanks. So there's been a lot of hype about Elbrus. Basically the punchline is, Elbrus we don't think is being used heavily anywhere in Russia. If it was, probably the people that I work for would be really interested in it, and I would not be talking to you at ShmooCon about it. So unfortunately, if you were hoping for all of the juicy secrets, Elbrus is really interesting, but it's not, as far as we can tell, it's not being heavily used in Russia. You'll see if you Google around, there's the stuff about this military laptop. There's a picture of it where supposedly, Russia ordered like thousands of them. It's not even. It's unclear if MCST even delivered those laptops or if anybody's using them at all. There was a crowd supply announcement, which was like kind of big. It was like, oh, wait, maybe we're going to actually be able to buy a motherboard. That went nowhere. This interesting, this quote here at the bottom, or from this magazine article over here, is they did a test with Russia's biggest bank, and to basically see if the bank could upload or could replace some of their Intel machines with these processors, and this was like the quote of the whole thing. Sberbank says, no, we cannot deploy Elbrus machines into our ecosystem, but we are pleasantly surprised that it works at all. Yeah, so that's really what it boils down to. In terms of just performance, Elbrus is just not at where, Intel, Xeon processors are, or something like that, right? But it runs Linux pretty well. So you can use them for Linuxy things, but not super fast. So when as a reverse engineer, like I look at all kinds of different processors. In my career, I've dug into all kinds of, embedded microprocessors to larger CPUs and stuff like that. And when we do that, usually what we do, the right way to do that, and when you're learning a new CPU, is to go out and get all of the documentation, data sheets that you can, right? And if you're working with a commercial processor, usually it's right on the website. You can download those things. You can look at the user guide or the programming guide, figure out all the instructions and opcodes, and away you go, right? Unfortunately, with Elbrus, they don't publish any of that information. They hold all of that information, as far as we know, under NDA. So what that means is basically we got a box that had Elbrus Linux on it, and it had some of their utilities like the LCC compiler and LDIS, which was like a text disassembler, and that's basically it. We haven't even been able to find, I was hoping for like leaked data sheets. I mean, anything out there, couldn't find it. The best thing that's out there is this programming guide, which is it was written in Russian, and it goes into goes into the assembly language a little bit. It goes into some concepts about how to optimize and things like that. But it's still not a traditional data sheet where it's like, here's the opcodes and instructions and the encodings. It's just kind of some best practices for programming. There is this thing called the OpenE2K project, and this is, I think it is, I can't tell if MCST is behind it or if there's kind of hackers that are interested that are kind of working on this, but it does have, you can get the Linux kernel source there, you can get binutil source code, QEMU if you want to play around with that. So binutils, basically, so all that together, this was kind of the setup I had for trying to explore this architecture. I really just had a Linux box, a compiler, and binutil source code. And thankfully, I was able to, with binutils, I was actually able to modify it. So in binutils is where we get like object dump from, right? So your basic text disassembler. And I was able to modify binutils so that it would tell me all of the subcomponents of the instruction, and that was basically what I was able to use for the rest of this talk. It'll be a little bit more clear as I get deeper into what's going on with Elbrus, what I mean there. Okay, so frac. Keeping with the theme of the talk, I need like the room to produce some like time travel like sound effects for me here, right? Thank you. Okay. So if you're familiar with any frac authors in the room? Oh, we got one over here. Oh, hey, Mudge, how's it going, man? This is awesome. Mudge is at my talk. All right. I'll try to focus and not freak out. So that guy over there, in the I guess the late 90s, I want to say. Yeah. So Mudge comes up with this idea of stack smashing, right? And he sort of wrote it up. And then a guy named Aleph1 in frac kind of took Mudge's concepts and wrote kind of the seminal paper, which was, smashing the stack for fun and profit, right? And people kind of, that's if you've never read about, how buffer overflows work, you go back to that article, which was in frac. A little while later, there was a guy named Rix who I have not, I've heard he's still around. Somebody said he might even be here. If he's here, I would love to meet him, but he's still around somewhere. And he wrote this paper called Smashing C++ V-Pointers. And so it's about similar concepts to smashing the stack, and it's basically just getting into using virtual function pointers in C++, overwriting them the same way you overwrite a return pointer when you're smashing the stack to do an exploit. So, and so this came out in Frac in the year 2000. So I decided to check out Rix's work and try to update it for modern compilers, and then use that as kind of just a pretext to explore the architecture. Again, because I only had a compiler, I had to kind of do it this way, where I just had an example and I kind of needed to compile something and explore it. Okay, so I kind of said that. I'm going to actually, I have time to kind of walk through exactly how how that vulnerability works. The cool part is that it still works on modern GCC. So this was actually why I went there. So in Linux, especially, well, it's Windows too, but in modern operating systems, stack smashing is a little hard because there's all these different mitigations that are designed to mess you up, right? There's non-executable stack, there is ASLR, and I actually saw some things about Elbrus that it was supposed to have some of those things built in, and so I decided, I was like, I'm just going to try to steer clear of that stuff and just play around with this C++ V-pointer concept, because everything about C++ V-pointers or exploiting them, still works, because you're not actually executing anything on the stack, you're just overwriting a function pointer. If you go back to Rix's article in Frac, which I highly recommend, he goes through, like, I want to say 3 or 4 different examples of how you can, of places where objects get created on the stack and you can overwrite the V-pointer. I just kind of zoomed in on one. But in my GitHub repo, there you can grab his, it's essentially his exact example, just updated for modern GCC, and you can run it and play with it, and away you go. Okay, so what does this, what does this look like? So if you're not familiar with C++, C++ is like C, but we create these things called classes, and classes are essentially just kind of like structures, right? If you're familiar with C, everything in C++ is basically just kind of created sort of as like a data structure. And we can kind of, the compiler kind of keeps track of all this stuff. So we've got a base class here, and this base class has a buffer, right? And so this is what we're going to eventually use to overflow. We've got this set buffer, function here, and it's basically just going to find the length at the first part of the message. So you can kind of see this is a vulnerable function to that buffer overflow. And we create a virtual function called print buffer. And then what we're going to do here is we're going to have 2 classes that derive from this base class, right? They're going to inherit, they're going to be child classes of the base class. What this does, since they both define this print buffer function, the compiler says, if I have an instance of base class, I don't know which print buffer function I'm going to call. If the compiler knows, for instance, if there's only one child and there's always one function that's going to get called, the compiler just put that address, that function right in there. But instead, the compiler says, I've got to keep track of this somehow. And because, it could be the myClass1 print buffer, the myClass2 print buffer, so I'm going to create a virtual function table, and that's going to be part of the object data structure. So this is the object that gets created for base class, right? Here's the buffer, and then there's a vtable pointer, and it points to a vtable. In this case, we only have one function in the class. It's print buffer, and so we're going to have a pointer to that print buffer, to that print buffer function. So you can see here, basically, because this vtable is next to this buffer, if we can overwrite into it, then we're overwriting that table, and we can now control what that object is going to call when it calls print buffer. Okay. So what are we going to actually do, with this exploit? So if you check out the code, there's this function called buffer overflow 2, and it's basically just setting up the overflow buffer that we're going to pass in and overwrite the v pointer on the stack. I'll get to that in a sec. If you see in kind of the main function here, we're going to allocate two objects onto the stack, right? And they're either one class or the other, right? And so you can imagine that data structure that we just showed gets allocated on the stack, and then when we write this, when we call this set buffer, buffer overflow 2 here is going to return the actual buffer, that's going to be passed into set buffer, and it's going to be overflowed, right? Here we're just like setting up a valid message. So this is just a valid message for the second object. But this first call here to set buffer is going to overflow and overwrite the v pointer of object 1. And so when we print buffer here, oh, sorry, I messed that up. Because we're actually overwriting the v table of the v pointer of the second object, right? Because the buffer, we have this like this, because the v table is in front of the buffer, we're overwriting the v table pointer on the second object, right? So the first call is going to overwrite the v table pointer for the second object, and when we call print buffer here, it's just going to print junk because it's going to print junk that was in the buffer, and when this call gets run, it's actually going to run our exploit entry function. And all we're really doing here in buffer overflow 2 is just setting up we're just basically setting up a fake v table, right? So once that pointer gets overwritten, it's now pointing to our exploit entry function. Things I had to update from Rick's example. So in 2000, we were using 32-bit pointers, and now we're on 64-bit architectures. So we had to update to 64-bit pointers. GCC moved where the v pointer was. So it used to be that the v pointer was at the bottom and GCC put it at the top. So it used to be you could just overwrite directly within a single object. You could overwrite the v pointer. Now you kind of rely on the idea that there's multiple on the stack, and then you can overwrite into the second one. He used this stir copy, and it turns out it worked because he was assuming that his 32-bit addresses didn't have any 0 bytes in them. And when you're working with 64-bit addresses, there's a lot more 0 bytes. So I had to kind of change what the vulnerable function. He used the stack-based shellcode, and I kind of cheated a little bit and just used a function address to make it interesting. In real-life exploitation, you would have to leak that function address, somehow, or leak the leak the stack pointer, to be able to make it work. Okay, so the cool part, so I got this working on GCC and on x86, and I ran it, worked, okay, and so I uploaded it to the Elbrus box, recompiled, and I'm thinking, oh, okay, I'm gonna have to figure out how the compiler is different and change things, but I compiled it here, and so I got myself an Elbrus executable, and I ran it, and it just worked. So never going to give you up is what my exploit entry function prints out. It's just called a printout. Thanks, going back. Here you go. Ooh, thanks. Directed. Amazingly, it just worked. Yay. And so it turns out that basically because their compiler is a direct port of GCC, and Elbrus is a 64-bit architecture, and it's little endian, everything about this just ported over directly to Elbrus. Okay, so that's the exploit, and let's talk about the Elbrus architecture, and we'll kind of use some disassembly from that to talk about Elbrus. So this is, I was telling you before, there's this idea like Elbrus is kind of a fossil architecture. Anybody worked with like DSP code before? See a few hands. How many people have worked? Looked at x86 disassembly? Okay, a lot of hands there. How about ARM disassembly? Okay, pretty good smattering there. So, if you've looked x86 or ARM, pretty in terms of how the instructions are encoded, pretty similar. x86 has these variable length instructions, and ARMs are fixed length, but Elbrus has this thing called very long instruction word, which is basically the idea that you are, instead of, and this is something that you would commonly see in DSP architectures. That's kind of where it exists today. It's this idea that that when you have a parallel superscalar processor, so you're doing out-of-order execution, you have multiple execution units executing in parallel, you're actually able to, in your instruction, kind of address each of those execution units in parallel. That's what it gets you. So there's 6 ALU execution units, and so you can actually have, you're essentially rolling up to six ALU instructions into one instruction. And what happened in, architecturally, when people had very complicated vector processing and matrix processing modes like you see in DSPs, they said, this will be really good. It's hard to do all of that optimization in silicon, so we'll let the compilers do the optimization. And that's why those things have very long instruction word. In Intel, Intel could be a very long instruction word architecture because it has this parallel processing going on, but basically the processor itself is doing the optimization of the instruction stream, trying to figure out what's the optimal thing to execute the stream of instructions in parallel. So Elbrus is really sort of this weird, this kind of a dead end sort of fossil that way, I guess. There are 64-bit registers. There's register windowing, which is another kind of weird concept that I'm going to go into a little bit. One of the most interesting things is that there's a separate stack for return addressing and register windowing, which is what allows them to be even more kind of secure against regular, buffer overflows with this procedure chain stack. I will say here that I don't have any idea how exceptions and interrupts work. That's usually something that's very important when we look at new processors. You want to look at, what's the code that executes on startup, how are interrupts handled? Have no idea. It's in the, we could look at the Linux kernel source code and kind of figure that all out, but we'd be basically looking at implementations of those things versus actual, documentation. Okay, here's the instruction encoding for Elbrus. It's actually not, it's not that complicated. This is basically the header, the instruction header that you use to kind of decode all of the other instructions that might be present. And we're mainly dealing with like these ALU, these ALU instructions. There's a few other types of instructions that I can see here. And basically all these fields are just kind of flags that show you, are there instructions that target these other parts of these other execution units. The instructions are called wide commands. I'm not going to try to pronounce that in Russian. It's something komandoi, but and so you have these ideas. So if the instruction is a word, then the individual instructions that are targeting specific ALU units, those are called syllables, right? So this is basically a header that tells you how to find the other syllables, the presence of the other syllables in the word. These are the ALU instructions, and what was interesting to me about this is it's a very small instruction set in terms of the number of instructions. Like this is literally all of the ALU instructions. It looks kind of RISC-like. It looks like ARM or something like that in terms of the number of instructions. Not a lot of, and so it's kind of weird. In a way, it's kind of weird. Like why do you need this very long instruction word optimization if you don't have that many types of instructions anyway? But that was sort of the design trade-off. Okay, just a little bit. This is just getting into some disassembly here of what this looks like. You can you can go into GitHub later and look, kind of compare the source code versus the disassembly to kind of see what's going on here. Basically, what I modified in binutils was I modified it to print out this instruction decoding information on the side here. And so it's actually printing out it's printing out the header syllable and then what the other syllables are. And we're basically just trying to show here that this is a load instruction. So this is like a basic load instruction. We're going to load double. We're going to use the execution unit number 0, and we're going to dereference like DR13 and put it into DR13, right? So this is just actually how it is dereferencing to find the function pointer for print buffer. Add instructions look really kind of complicated, but this instruction is just saying take a 16-bit immediate and add it to DR13 and place it in DR1, and we're going to use ALU 0 for that. Right? So that's just real basic, add and load instructions in Elbrus. Okay, register windowing. So register windowing is a really weird concept that is. And you got to be careful when you talk about, when you're talking about Windows and Russia. If you're in Russia, you don't want to stand close to, a window. I assume it's the same on Elbrus. I don't know. The idea with register windowing is it's a lot like how stack memory works and if you think about how stack frames work. You have, if you've ever done a stack trace, you kind of unwind the stack and you find the local variables and the return address of each of each frame. Register windowing is the same concept, just applied to the registers themselves. So if you think about in x86, or ARM, it's both the same way. Whenever you do a call, you're transferring a bunch of things into registers, and you're probably saving off registers that aren't supposed to be overwritten. And then you do your function call, and then at the beginning of every function call, every function is kind of moving those things around, right? They're grabbing out the parameters, and maybe they're saving off the old the old stack pointer, stuff like that. Register windowing basically says, well, what if we can kind of get rid of that instead of having to do all this shifting around of registers on the stack, and then the functions pulling them off the stack and that kind of thing. What if we can just keep them in the registers, and then we basically, when we call a new function, it's got a separate set of registers that includes an overlap with the previous function set of registers, and then some more things, right? So we have, a function here has this register window. There's an overlapping parameter area, and when we call this function, we basically say, I want your register 0 to start here at the bottom of the parameter area, and then it can just access them, as registers. And the nice part is then when we return back to this function doesn't have to save off any state or anything, because all these registers that are back here or couldn't be touched. Right? So it's a neat kind of thing, but it makes the Elbrus disassembly pretty hard to look at, because you're as a reverse engineer, you're used to kind of seeing I have this set of registers and they're named RAX, RBX, RC, right, or R1, R2, R3. But what's happening is that here you've got DR0 in function 1 and DR0 in function 2, and they're actually different things. So it's a little bit weird to kind of keep track of. Do they actually get performance enhancements out of that? I don't know. I'm not going to walk through this fully, but it's there. So this is, I actually, just to kind of prove to myself that I knew what was going on, with the register windowing, I actually walked through a particular function call to understand all of the moving pieces in that, in that call. And basically, the other part of this is that not only are there these windows, there's also this separate base register. So each function can use a base register and move that base register to point to a different place in the window. So anyway, yeah, it's pretty complicated. This is what I found, kind of one of the most interesting things when I was exploring Elbrus. So you can check that out, as you like. Another interesting thing about calls and branches in Elbrus. So this is I'm just showing you how the class 1 constructor is called here. Calls actually take place in 2 stages. So x86 ARM, we just do a call, right? Call subroutine, away we go. On ARM, we're going to do a branch and link, right? Branch and link to the subroutine, and we just go there. Part of the whole idea with this this complicated instruction set and trying to get more optimization out of that was the calls are actually broken up into two separate operations. So we have this disp, this disp instruction basically tells the pipeline, hey, we're about to transfer to this address. And basically what it allows if you've studied any of this in x86, whenever you do a call, it's a lot of stuff going on in the processor to kind of set up, save all the state off and then, jump somewhere, right? So this basically tells the pipeline, hey, we're about to do a call, get ready, and then later on we actually do the call and the control transfer actually happens. There's a separate instruction just called CT for control transfer. This is a little bit about the separate call stack that I mentioned. There's this internal register called the procedure chain stack pointer, and we get this type definition out of the Linux source code, but it's not really it's not really helpful in kind of understanding what's going on. So I think that's a really important area of exploration for future, assuming that we actually want to exploit some of these things. Okay, yeah, so what are we actually going to do with Elbrus in the future? It's really uncertain, right? The future of Elbrus is uncertain, I think, as is all of the entire, Russian computer industry and economy, right? It kind of remains to be seen. I think it's still possible. So, a lot of times that these processors will get used in like political projects or like high visibility projects where the idea is, I want the national processor included and I make a big deal out of that. So it's very possible that Elbrus will show up in something interesting in the future. I think it'll just be really interesting to see, we're kind of constantly following what's going on with China and Taiwan and what's going on, both in our country with, building back, the domestic semiconductor industry, and then how is this going to affect, how does this affect Russia, because they're trying to, build these things somehow. So really a lot of stuff up in the air. No great, no great immediate next steps, but a lot of things to kind of, watch out for. Okay, so I just, thanks for everybody for coming to my talk. Thanks for getting through all that deep technical stuff. Thanks for geeking out with me a little bit. I want to say thank you to my good friend, good neighbor, who many of you probably know, who lent me access to the Elbrus machine. I want to say thanks to Moyux up at NYU, who he actually was looking at this stuff, and I got to talk to some of his grad students who were looking at this as well. Bunch of folks at APL, so Lynn, Paul, Ryan, Molly, Mo, thank you at APL. I want to thank you to my family. I was saying thank you for being gentle with those, but that looked really like a violent reaction there. Yeah, so thank you for gently pelting me with Shmoocon. That was a good one. I think you took off the. Yeah, that's good. Okay, and just wanted to say thank you to Heidi and Bruce and for all of the volunteers at ShmooCon. I was really sad to hear that news yesterday. Still kind of processing it, but just really, really thankful for the last couple of years to be able to speak and be a part of this. So, yeah, thank you, everybody.